Hello students, welcome to grade 12 chemistry revision lesson on phase equilibrium. At the end of this lesson, you should be able to tell the relation between kinetic energy, force of attraction and states of matter, define phase, components and degree of freedom, explain the relationship between vapor pressure and boiling point, describe how a phase diagram shows a phase of a substance at different conditions of pressure and temperature, use a phase diagram to determine melting point, boiling point, critical temperature, critical pressure and triple point of a substance. Students, if you are ready, then we will get started. Force of attractions, kinetic energy and state of matter. What is the relation between force of attractions, kinetic energy and state of matter? At a very high temperature, kinetic energy is greater than force of attraction. Kinetic energy is greater than force of attraction. As a result, molecules are far apart. Kinetic energy makes molecules far apart. The substance does not have a definite shape or volume. This state is known as gaseous state. Students, at high temperature and low pressure, a substance will exist in gaseous state. 2. At a very low temperature, the molecules possess small kinetic energy. So, kinetic energy is less than force of attraction. As a result, the molecules are held together. Force of attraction held molecules together strongly, and the substance has a definite shape and volume. This state is known as solid state. Therefore, a substance will exist in solid state at high pressure and low temperature. 3. At intermediate temperature, at intermediate condition, the kinetic energy and force of attraction match each other. You see, match each other. Kinetic energy is approximately equal to force of attraction. As a result, the molecules are held together but not strongly, so that the substance has a definite volume but no definite shape. This state is known as liquid state. Note that a substance will exist in solid states at high pressure and low temperature. A substance will exist in gaseous states at high temperature and low pressure. At intermediate condition, a substance will exist in liquid state. Common terms: phase, component and degree of freedom. What is a phase? Phase is defined as it is part of the system which is physically and chemically homogeneous and separated from rest of the system by a discrete boundary. Look at this system. A mixture of water and chloroform has two distinct layers, one water and the other of chloroform. Therefore, the number of phases of this system is the number of layers, which is 2. The simple rules for determining the number of phases. How can we determine the number of phases for a given system? These are the rules. 1. Pure substance present in one state of matter constitutes one phase. You can take carbon dioxide. Carbon dioxide gas is a one phase system. Water, liquid, H2O is pure substance. Liquid is one phase. Therefore, pure substance present in one state of matter constitutes one phase. 2. Same substances present in different states of matter. Present in different states of matter. For example, water liquid, water H2O liquid in equilibrium with water gas, H2O gas, you see. The same substance present in different state of matter constitutes different phases. Therefore, this system has two phases, liquid and gas, but the same substance, which is water. Ice and water are two different phases of water. Ice is solid water, H2O, solid water in equilibrium with water liquid, H2O, liquid, you see. The same substance present in different state of matter constitutes different phase, which is solid and liquid. Number 3, a mixture of gases constitutes one phase. A mixture of hydrogen, oxygen, and methane gases is a one-phase system because this is homogeneous. Homogeneous is one phase gas. 4. A homogeneous solution is a one-phase system. Solution of sodium chloride in water. If sodium chloride dissolves in water, it forms a homogeneous solution. Aqueous solution is a one-phase system. 5. For immiscible liquids, liquids which cannot dissolve with each other, the number of layers formed is equal to the number of phases. A mixture of oil and water. Oil and water are immiscible liquids. They form layer. How many layers? 2 layers are formed. Therefore, the number of phases equal the number of layers formed. For this system is 2. A two-phase system, P equal 2. For this number of phases, P equal 1. For this, a mixture of hydrogen, oxygen, and methane gas is homogeneous. P equal 1. It's a one-phase system. Number 6, for solids, each chemical species is a different phase. Different allotropic forms of the same substance constitute different phases. For example, a mixture of powdered sodium chloride, look, powdered sodium chloride, this is one phase, and potassium chloride, another phase. Therefore, for solids, each chemical species is a different phase. Now this system is a two-phase system. Number of phases, P equal 2. For solids, each chemical species is a different phase. Different allotropic forms of the same substance constitute different phase. Diamond and graphite are different forms of carbon, so they are different phases. Components, denoted by the symbol C. Components is the chemically distinct quantity in the system. You see? The number of components in a system is represented by C. When no chemical reaction in the system, the number of components is equal to the total number of chemical species present in the system. When there is no chemical reaction take place in the system, the number of components is equal to the number of chemical species present in the system. You can take this as an example. An aqueous solution of sodium chloride. Sodium chloride is dissolved in water. There is no chemical reaction between sodium chloride and water. This is a solution. Therefore, the number of components is equals to the number of chemical species present in the solution, which is sodium chloride and water. The number of components C is 2. The number of components C is 2. B, a mixture of hydrogen, oxygen and methane gases. Again, there is no chemical reaction between the species. The number of components is equals to the number of chemical species present in the system. How many chemical species are there in this system? Hydrogen, oxygen and methane, 3. Therefore, C is equals to 3, number of components. C, ice floating on water, solids in equilibrium with water, liquid, you see, ice floating on water. There is only one chemical species in this system, that is water, H2O. Therefore, the number of components is 1. C is equals to 1. Is only one chemical species. Degree of freedom denoted by capital F. This is the minimum number of variables required to describe each component in each phase of the system. Degree of freedom is the minimum number of variables that required to describe each component in each phase of the system. It is represented by F. Since only temperature and pressure are required to describe a pure substance, the degree of freedom of pure substance is 2. Degree of freedom for a pure substance is 2. Why? Because two variables, which are temperature and pressure, are required to describe it. All the 3 states of matter of a substance coexist at a point known as triple point. At triple point, 3 states of matter coexist. The triple point has a fixed value of temperature and pressure. Therefore, no variable is required to describe the system. Now the system is invariant. No variable is required to describe. Phase rule. It relates the number of phases and components to the degree of freedom by the following equation. You see, degree of freedom F equal number of components minus number of phase plus 2, where 2 is the two variables temperature and pressure. Now this is Gibbs phase rule equation. Allows us to calculate number of degree of freedom. For example, calculate the degree of freedom for one component system, C equal 1, and for P equals to 1, one phase system. You can take water liquids, for example, water liquid, H2O, liquid. What is the degree of freedom for a one component system of phase 1 for P equal 1? Now, degree of freedom F equal C minus P plus 2. C here is 1 minus P is a one phase system, P equal 1. 1 plus 2 equal 2, you see. What does this mean? Two variables are required to describe this pure substance. You see, degree of freedom F equal 2. Temperature and pressure are required to describe this pure substance. Now this system is bivariant system. Bi means 2. Two variables are required to describe a one component system with phase equal 1. B, P equal 2. Now, what is the number of degree of freedom for a one component system with phase 2? Now, the degree of freedom F equal C minus P plus 2 equal C is 1 minus phase is a two phase system, For example, you can take this as an example. Water, H2O, liquid in equilibrium with water gas, H2O gas, you see, is a two-phase system, liquid and gas. But C is 1. Number of components is 1. Is only one chemical species, is water. Therefore, F equals C minus P plus 2 equal 1 minus phase is 2 plus 2 equal 1. Now this system is monovariant system. Only one variable is required to describe this system. What does this mean? If temperature is known, then pressure is fixed. Or if pressure is known, temperature is fixed. To describe a one component system with phase 2, only one variable is required to describe it. We call it monovariant system. Same for P equal 3. What is the degree of freedom? Phase equal 3. For example, you see, phase 3P, water H2O solid in equilibrium with water liquid, H2O liquid in equilibrium with water gas. Now, the number of components C is 1 because there is only one chemical species, one pure substance, which is water. C is 1. Phase P is 3. You see, number of phase is 3. Solid, liquid, and gas. Now calculate degree of freedom for this system. Degree of freedom F equal C minus P plus 2. C is 1. One component system. 1 minus phase 3 plus 2. See? 1 minus 3 is minus 2 plus 2 is 0. No variable is required to describe this system. We call it invariant system. Invariant system. What does this mean? This system has fixed temperature and pressure. Fixed temperature and pressure. For P equal 4, degree of freedom F equal C minus P plus 2 equal C is a one component system. 1 minus phase 4 plus 2 equal 1 minus 4 is minus 3 plus 2 is minus 1. Is impossible because degree of freedom cannot be negative. Therefore, a maximum of 3 phases can be coexist at triple points. Phase diagram. Phase diagram for a one component system is a graph. Which shows variation of pressure of the system with temperature. Look at phase diagram for one component system. For example, phase diagram of water, one component system. Phase diagram of water, H2O. As we know, one component system has only one chemical species, pure substance, and it can be described if the temperature and pressure of the system are known, because degree of freedom for a pure substance is 2. Temperature and pressure are required to describe a one component system with P equal 1. Under specific conditions of temperature and pressure, the system can exist in one phase, or 2 or 3 phases may be present in equilibrium. Characteristics of a phase diagram for pure substance. 1. Temperature is plotted on x-axis. You see, for a phase diagram, temperature plotted on x-axis and pressure on y-axis. Pressure plotted on y-axis. The different regions of the graph, you see, different regions of the graph represent different phases. This is phase of water, which is solid ice water. in which the substance can exist. We know that a substance will exist in solid states at high pressure and low temperature. Now this is solid water, which is known as ice. A substance will exist in gaseous states at high temperature and low pressure. This is water in gaseous states, water vapor. See? At intermediate condition, a substance will exist in liquid state. This is liquid water. Therefore, the region A or B is solid water, which is ice. B or C is liquid water. A or C is water vapor, water in gaseous states. The boundary between the phases is represented by a line. You see, the boundary between ice and water vapor is sublimation curve. We call it sublimation curve. Sublimation curve. This curve has a positive slope. What does this mean? As pressure increase, sublimation of ice also increase. Positive slope. The boundary between solid water and liquid water is melting point curve. Melting point curve. Now this curve has negative slope. What does this mean? As pressure increase, melting of ice decrease. The boundary between liquid water and water vapor is vaporization curve. Vaporization curve or boiling point curve. Boiling point curve. It has a positive slope. What does this mean? As pressure increase, boiling points of the liquid also increase. On transition line, two phases are at equilibrium. On transition line, two phases are at equilibrium. On melting point curve, you see, on this line, water, solid, H2O, solid, ice water is in equilibrium with water liquid, H2O liquid. On sublimation curve, on this line, water solid, ice water is in equilibrium with H2O gas, H2O solid in equilibrium with water in gaseous state. On vaporization curve, on this curve, water liquid, H2O liquid in equilibrium with water gas, H2O gas. A triple point represents three phases at equilibrium. At triple point, this is triple point. At triple point, three phases are in equilibrium. Yes, the three phases are this: water, H2O, solid in equilibrium with water liquid in equilibrium with water gas. At triple points, all three phases coexist, you see. Solid, liquid, and gas coexist. Students, in our today's lesson, we defined a phase. Phase is part of the system which is physically and chemically homogeneous and separated from rest of the system by a discrete boundary. Number of phase is denoted by the symbol P. We discussed rules for determining number of phase. Again, we defined components. Components is the chemically distinct quantity present in the system. If there is no chemical reaction take place in the system, the number of components is equal to the number of chemical species present in the system. We learned how to calculate degree of freedom for a pure substance having phase 1, phase 2, phase 3, and so on. We also discussed phase diagram of water. This brings us to the end of our today's lesson. Until next time, goodbye.